Hello, today we're going to be talking about BFS and DFS. BFS and DFS. BFS stands for breadth, first search. And DFS is depth, first search. Now, BFS and DFS both generate trees. They both generate trees. What is a tree? Now, we've talked about graphs and graph structures in a previous video, and that will be linked in the description below. So in a graph of nodes and edges and connections, we have a tree. A tree is connected, so it's connected. Tree is connected. It has, if n were the amount of nodes, it would be n minus 1 edges. And then there are no cycles. There are no cycles. So if we were to have a graph here, just nodes and connections, we see that this is not a tree because there's a cycle here. There's a cycle here. If we were to get rid of the cycle, this is a tree. We can also see that this is a tree. You see that this is not a tree because we have a disconnected component here. So if we connect that back, that's also a tree. We can also see that we have, how many nodes do we have here? How many nodes? We have 1, 2, 3, 4, 5, 6. So if n were the amount of nodes, we have 6 nodes. And our connections, 1, 2, 3, 4, 5. M is the amount of edges we have, and that's 5, which is equal to n minus 1. These brackets symbolize the number of nodes we have. Now let's compare BFS and DFS. Let's start with BFS first. What does BFS say? BFS says, explore my siblings first, before my children. So if we were to draw a simple graph, let's use a binary tree first here to illustrate. Remember that BFS can be run on any type of graph structure, just that we're using a binary tree first to simply illustrate what's going on. It'll be easier to see. Now remember, we can separate this tree into levels. And BFS uses and implements a queue. So let's give names to all these nodes: A, B, C, D, E, F. Now we'll start by evaluating the root node, the starting point of our graph. And we're going to say, okay, evaluate S. So we're going to throw S into the queue. And remember, a queue is first in, first out. As like if you're going to the cafeteria, if you're the first in line, you'll be the first to be served. So we'll come in with S, and S is here, and we're going to evaluate S. And we're going to say, okay, S, what are your children? S is going to say, A is my child and B is my child. We'll put A and B onto the queue, and then we're going to pop S off. And now we're going to go ahead and then evaluate A. We're gonna look at the queue. We're gonna say, okay, A is first. A, tell me, what are your children? A is going to say, my children is C and D. So it's going to queue C and D. And then we're done evaluating A. Then we're going to evaluate B. B is going to be like, my children are E and F. So we're going to put E, then F. That's an E, then F onto the queue. And then we're done evaluating B. And so forth. We're going to see that C here, does not have any children, D does not have any children, E does not have any children, F does not have any children. So we're going to evaluate these. We're going to evaluate C, then we're going to evaluate D, evaluate E, then F. And we can see that the order we traverse these in, and evaluated them, and evaluated these. So every time we evaluated and popped them off the stack, or queue here, this is a queue, not a stack, we got this sort of structure. We sort of maintained the tree-like structure using BFS. So we traversed 1, 2, 3, 4, 5, 6, 7. So really in this sort of level order going this way. And that is BFS. So now let's run DFS on a binary tree. Let's run DFS on a binary tree. S, A, B, C, D, E, and F. This is an E. On this binary tree, we're going to use a stack. DFS uses a stack. So this means if I were to stack up a bunch of plates, if I were to stack up a bunch of plates, and I'm going to clean them, the first plate in is the last to be cleaned. So if I'm like, okay, I'm going to start at the top, and I start cleaning them, and I make my way all the way to the bottom, the last plate, or the first plate I put in, is the last plate I'm going to clean. So this is how it's going to work. First, DFS pre-populates the stack with our starting node, S. So we're going to start it with S. And we're going to ask S, what are your children? We're going to evaluate it. I'm going to put a little V here. I'm going to evaluate it and ask S, what are your children? S is going to say, well, my children are B and A. My children are B and A. And at this point, we're starting to sort of build this sort of tree here, or B and A. And then we're going to look at the top of the stack. After asking that question and after filling it with what could have possibly been filled with, we're going to look at the stack again. We see A is there, and we're going to evaluate A. And once we evaluate A, we're going to say, okay, A, what are your children? A is going to say D, then C. D, then C. And then we're going to look at the stack again after asking that question and populating it, and we're going to evaluate C. We're going to evaluate C. And C is going to say, well, I don't have any children. So we populate the stack with no children. Then we look at the stack again after asking and populating the stack. We see that C is at the top, but we've already visited C. So we're going to pop it off the stack. We evaluate D. We finally reach D. We evaluate D, and we say, what are your children? It has no children to give, so it populates the stack with nothing. We look at the stack again. We see A. We've already visited A. We look at the stack again. We see B. Now, you can pause the video here and guess and try what's going to happen after this. All right, we're back. So we evaluate B, and B says, well, my children are F, or F and E, or F and E. So we just evaluated B, and we're going to say, okay, we're going to evaluate E now. We're going to evaluate E. We finally evaluate E. The same thing happens. We evaluate E. It gives nothing. We take it off. We evaluate F. So we finally evaluate F. It has nothing to give. So we see that we've already visited it. We look at the stack again. We already visited it. We already look at the stack again, and we visited it. So in both cases here, DFS does create a tree as well, though the order of traversal is different from BFS. So let's draw BFS again right here. So we're going to do BFS in red, and then we're going to do DFS in yellow. This yellow is orange. So we traversed 1, 2, 3, 4, 5, 6, 7. While BFS said 1, 2, 3, 4, 5, 6, 7. So DFS here really took sort of this sort of path. Went all the way around, it sort of took that path. And we still get a tree out of this. The DFS said it's going to go by level. So it sort of took this path. It took this zigzag. While DFS took this sort of snake, if you will. And that's DFS. So to start talking about the different classification of edges that we have, we need to sort of start thinking about time. So let's start thinking about time. So let's draw an arbitrary directed graph here. So let's get a directed graph going. Directed graph. We're going to use this example. And using this, we're going to arrive to all the possible classifications you could get in a directed graph. Let's see, a directed graph for DFS. So let's name these. So S, A, B, then C. Now let's add our stack, the stack we're going to use. You can pause the video and try to see what you'll get out of a DFS traversal. But I'm going to go ahead and start writing this times table that we're going to use to start tracking the time. So we're going to have a start time, and then we're going to have a finish time. And we're going to start the clock at 0, and we're going to pre-populate the stack with S. And we're going to start with start and then the finish time. So this is how we're going to populate these stack members. And we're going to track S, A, B, and C. S, A, B, and C. So let's start this out. So we start at 0. So we give S a 0. And we're going to ask S, what are your children? It's going to look at itself, and it's going to say, well, I'm not going to add myself because, I've already been visited, I already have a start time, so I'm not going to add myself to it. So I'm going to say, okay, well, I have C, I have B, and I have A, and then that's going to be the end of it, and we're going to look back at the stack again, and we're going to ask A, what are your children? So we increment the timer. So every time we evaluate, so we evaluated S, and we increment the timer. We're going to ask A, we're going to evaluate A, increment our timer. What are your children? A is going to say, well, my children. We're going to see B here. My children is B. My child is B. We see that we have B twice here on the stack. This is going to show us sort of the diverging or different classifications that we're going to get. But let's start. We're going to look at B. We're going to look back up. We're going to look back at our stack, and we're going to see that, well, B's here. Let's evaluate B. Let's increment our timer. So let's start filling in our table here. We're going to ask B, what are your children? B is going to say, well, I have no children. And we're going to say, okay, we're going to look back at the stack. We're going to see B, and we're just going to give it a finish time. We're like, we're done with you. Let's give you a finish time. And we're going to take you off the stack. We're done with you. We're finished with you. Then we're going to increment the timer after we're finished with B. And we're going to look at A, where we're saying, well, we already gave you a start time. I'm going to give you a finish time. You're going to get 4. And I'm going to kick you off the stack. This is our first classification that we're going to get. If you look at B, we already have an entry. Now, all the entries we've added so far are tree edges. So everything that ends up on this table, on our left here, everything that ends up on this table is a tree edge. It's part of our tree edges we have going on here. Let me draw them real quick. So this is a tree edge, this is a tree edge. That's what we sort of discovered so far. And we're going to look at this B here, which is this edge over here on the left, this edge, and we're going to say B. This looks like a forward edge, We're not going to use this B, but we can classify what kind of edge this is. We call this a forward edge. We can call this a forward edge because it's skipping. You see that it skips. It's skipping A to get to B. So it's skipping a node in the tree. So this A is part of the tree. So these edges are part of the tree. It skips a node in the tree to reach a further descendant in the tree. And we can classify this by saying this S going to B. So this edge right here, when S is going to B, the start time, we say this is the start time and this is the finish time here at the bottom. The start time of S is less than B, The start time of S is less than B. And we see that the finish time for S is going to be greater than B. It's going to be greater than B. You see that B here is 3, and we're currently at 5 on the timer. So S must have a larger time. Like if you were to give it a time now, it would be 5 or some other number. So B here is going to have a smaller finish time, and S is going to have a larger finish time, and S starts earlier. So S right here starts earlier, and B here finishes earlier. That's how we know we got a forward edge. And tree edges also have this sort of same classification. The only difference is that, sort of looking at it node-wise, that a forward edge isn't part of the tree, and a tree edge, is part of the tree, and a forward edge, sort of to drill this back into the mind, that a forward edge is skipping a node. So now we can look at C. Now. The time is now 5, so we add 5. And we ask C, what are your children? And we're going to look at 2 edges here. We're going to look at B. Let's first look at B. This edge we're not going to add to our tree, as we've already looked at B. We've already visited B. So in the forward edge, it was in the stack. It was already in the stack. We see that C here, C to B, this edge, we haven't added it to the stack yet. It's not in the stack. It's currently not in the stack, but we want to add it to the stack. And this one is called a cross edge in particular, because if we draw this sort of tree we have right now, we're going to need a little bit more space. I'm going to draw it over here. If we draw the tree we have now, S, A, B, C, this edge right here seems to be crossing. We have our branches here. We have a branch, this branch and this branch. Seems to be crossing a branch to a node. So it's C. The endpoint of C is a node in the tree. So it's a node in the tree that is not a parent of C and is not a descendant of C. So in the tree, B isn't a parent or descendant. See, look. B isn't above it, and B isn't below it in the tree. There's no orange line we have here, no yellow-orange line that's connecting to C in the tree. Therefore, this edge that we're not putting in the tree is a cross edge, Now, we're going to have, so let's start drawing them out a little bit over here too, to make it sort of apparent. So forward. This last edge we're going to look at here, this last edge is a back is a back edge, because we're going back to an ancestor that's in the tree. This is a back edge. Remember, these edges are not in the tree. This edge is going back to an ancestor in the tree, Here, over here, S pointing to S, there's no classification for it because, it's not greater than or less to than in sort of starting times or finish times. So to iterate the cross example, so we have C going to B here, we see that the start time for C is greater. So let's start writing these in. 5. The start time for C here is greater than B, because see, we have 5 and 2, so 5 is larger than 2. Then the finish time is also greater. We see that B is 3 here, and we haven't had a time yet for C, so it must be larger. It must be larger than B. So this is a cross edge, and I'll write all of these in one place in just one moment. And let's talk about the back edge. The back edge, we can see that it's C going back to S. We see that the back edge, the start time for this is greater because we looked at it later in our traversal, and the finish time is going to be less than S. So you see here that C, we haven't put this in yet, but we're going to yet traverse back to illustrate this. Let's finally give C its finish time, take it off the stack. So we'll give C 6 here, and then we're going to increment the timer to 7, and we're going to give 7 to S as the finish time. So we can see that the finish time for C is less than S. This is a back edge going back to an ancestor. Okay, now let's try the same example, the same directed graph. Remember, we're doing this on a directed graph. This is important because it changes between directed and undirected graphs where we don't care about the direction. So now, if you would like to pause the video to sort of try this yourself, to start this off yourself, we're going to be using BFS on this directed graph. So now let's start and populate our queue with S. Now we're going to ask S. So we start out with S. We're going to ask S, what are your children? And S is going to say, well, my children are A, B, and C. And then we're going to go ahead and say, okay, we're done evaluating you. You can head off. And then we're going to go ahead and then evaluate A. We're going to evaluate this edge going down to A. So we're going to evaluate this A right here. And we're going to say, hey, what children do you have? And it's going to mention this edge right here, this B. And we're going to put that in the back of the queue. So we're done evaluating A. We're going to be evaluating this next edge right here, this edge to B. So that means our next edge is actually this one in our tree. And this one right here. Then we're going to ask B, do you have any children? B is going to say no. Okay, so we're going to stop evaluating you and move to the next person. C is going to say, well, I have this connection B, and then I have this connection S over here, so I'm gonna put that at the end of the queue. I'm gonna say B, and I'm gonna say S. And we're gonna stop evaluating C, and we're like, okay, we're done with you now, C. So we're gonna put C over here, and now These are where our new edges are going to come in. We're going to evaluate this B. This B came from our A. This B came from our A. And it's talking about this edge right here. This edge right here. Talking about this edge right here. What type of edge is this? What type of edge is this? Let me draw it in a different way. Let me draw it in a different way now. What type of edge is this? What type of edge is this? This is a cross edge because we're going to an endpoint B that is not a parent and is not a child in the original tree graph. Everything in yellow is the original graph. B isn't connecting to A in any sort of way. So this is a cross edge. We're crossing between branches. Now, this C right here, let's see, what type of branch is this then? This is also a cross branch. And now, finally, so we just evaluated these two, A's connection and C's connection. C announced this last connection. What is this last connection here? This is a back edge because we're going back to an ancestor in the original tree, And remember, all these green edges are not in the tree. These are not added. So, for directed graphs, we have that BFS can find back edges, cross edges, and of course, tree edges, which are all the edges that are in the tree. That is BFS on a directed graph. Now, I'd like to state one more thing. That forward edges are not possible. Forward edges are not possible in a directed graph for BFS. Because for forward edges to happen, they're the same thing, sort of the same classification time-wise as tree edges, but they're not in the tree. So let's say S, A, B. So this sort of traversal would have to happen first for there to ever be some sort of jump. But the way BFS, as it's going through level by level, there's no way it can have sort of this jumpy nature to it for us to dig deeper into children before exploring the most outermost path we could be taking. So for that reason, we cannot have forward edges in a BFS traversal on a directed graph. Now here we have an example. With an undirected graph. So there's no directions happening here. We're going to try this with a DFS. And we're going to try this with BFS. Try this with DFS and BFS. So you can pause the video here and try it yourself. Okay, let's think about our stack here. So we're going to start with S. And we're not going to add S itself, but depending on which path you take, you're probably going to get something different. Let's, for the sake of simplicity, just take the middle path. Let's take the middle path. So we have S going to A, S going to A. Then we're going to have S or A going to B. And B can take two paths. E or B can either go back all the way to S, which would be a backwards edge, or it can go to C. Now, what are C's options? Here? C can either go back to S, or it can go back to S. So here we just have more back edges. And it turns out that DFS on undirected trees, or undirected graphs only have tree edges and backwards edges. Let's try BFS here. So BFS, we start with S. Let's look at our Q. I think it would be more helpful to draw the Q here. We look at the Q. Let's say we start with S, We ask S, what are your children that haven't been visited yet? This doesn't have a classification, so we're not really going to be putting it in the queue or examining it. So we're going to say, okay, we have A, B, we have C, then C. We have these two C edges here. We're probably going to only be choosing one of those. So look at this, and we're going, okay, let's look at S. Take out S. Let's look at A. We're looking at A. We ask A, what are your children? A is going to say, well, I have a child B. I have a child B. I can go back to B. You're going to put that back at the end of the queue. We take out A. We look at B again. So the B A was talking about was this edge. So we're going to look at B, which is this edge right here. We're going to ask B, what are your children? What are your children? And we're not going back to S. We just came from S. And we can talk about C. So we put C at the back. We can go to C. We look at the actual C. So one of these C edges here. And the only thing that we could possibly get here when C announces, when we're going down this sort of path, is that C can sort of just announce, well, B is my neighbor here, or that B is my neighbor here from A. These are only going to really create, cross edges. These are going to really create cross edges. So typically in BFS, we're only getting tree edges, and possibly cross edges. One could look and say, well, I could get a back edge out of this. But that's perchance because we have these double, usually in undirected graphs, you don't see these double sort of like connections. So C could possibly announce a back edge, but depending on the way you've set up your BFS, you can get a back edge, but typically in literature, when you're going to be on a test question, you could either get a tree or a cross edge. And even these cross edges can be dependent on the implementation, because you can say, well, I'm not going to add those back to the queue because we've already visited them. But you can be safe to say that you can discover these cross connections. In your tree. So for undirected graphs, for DFS you have tree and backwards edges, and for BFS you have tree and cross edges. And that's what you get for undirected graphs. I'll write out both directed and undirected right next to each other. So again, to put this all together, DFS, or let's do it like this. We can do undirected on undirected. We have for BFS, we have tree. And cross edges. For DFS, we have tree and back edges. Now for directed, we have for BFS, we have tree. We have back edges, and we have cross edges. No forward edges. For DFS, we have the whole shebang. We have tree, forward, back, and cross. And to remember our times, let's write out our times here. So for our times, for start, for start and finish. For start and finish, we have, let's just use for trees. For trees, we have that, remember the U and V notation, where you need the starting point. So for U, U tree is less than V. So again, this notation where U is going to V, and we have a start and finish time, and we have a start and finish time. U is less than V, and U's finish time is greater than V. As in a tree, when we're traversing, we're increasing that start time. And then as we bubble back up, we're finishing. So it's going to get larger and larger and larger. So the start should have the smallest start and the largest finish time. That's the starting node. So that's how you can derive that. And now let's go for forward. Let's talk about the forward. So for F, the forward, we have U. So U it's the same thing. The only difference, you remember, forward edges, they have some sort of intermediate thing they're skipping. So if there's like a U, then there's a W, then there's a V, there's a V. U is skipping to V. So here is our forward edge. And then we have our back edge, which was the back edge would be U is greater than V. As our start time, for us to go back in time, we have to have started later. And then that means that our finish time is going to be less than V, because for us to go back, we have to wrap up things below before we go back. So our destination is going to be larger. So let me just draw it here on the side. So V, this was in the past. And U is going towards it back. So this was past. So like already visited. So this is a back edge. And again, a forward edge, we have not the forward edge, the cross edge. We had that U is greater than V, and that U is also greater than V. As we're talking about different sort of branches here, sort of there's a lot of things going on there. Different branches. And it's sort of crossover. So this is V, this is U, and remember that this is actually part of the tree. And this V here, or this U here, starting to mix up my U's and V's now. This U here is going to something that's, this cross edge is not in the tree, but it's going to a node across a branch that has already been visited. So visited and finished. So it's all processed and done, but we're somehow just crossing over to some alternate timeline and saying, oh, I'm crossing over. So this is a cross edge. The V in the original table is not a parent or child of U. There's not a yellow line connecting V and U. It is not in the original tree. This is a cross edge. And those are all the classifications that you need to know for BFS and DFS. So now let's actually jump into some pseudocode for BFS. So BFS is going to take two arguments. We're going to need that graph structure, and we're going to need a starting node. Let's take out our example again. Now, we need to understand sort of, or just let's take out a regular binary tree. Now, we need to understand first, what are we doing before we start coding? What are we doing before we start coding? We know we used a queue. We know we used a queue. So let's go ahead and initialize a queue. Let's call it queue. Probably going to run out of space here in a moment. So let's call it queue. And let's give it a queue. So let's just say queue. This is going to instantiate a queue. We use this arrow here to indicate, normally we'd use plus, not plus, an equal sign, but here usually in pseudocode, very often in literature, you will see instead of the equal sign, there's an arrow to indicate this queue is going inside this queue. Well, this variable is going inside this variable. So we are going to continue. So the next step is, we usually start pre-filling. Say this is our starting node. We usually start pre-filling our queue. So let's start by pre-filling our queue. Let's insert into our queue. Let's insert that S. Give me that S. Let's see. Insert the S. Now, we are going to need some sort of that tree. We had a tree that was being created from this, and we want to sort of create that sort of structure. We could go ahead and, create a tree right here and sort of starting to create that sort of structure. I'm going to give myself some more space and start instantiating it over. Let me instantiate it over here. Let's say colon. I'm going to create a tree, and this is going to be a hash structure. So the keys are going to be right here, and the sort of neighbors are going to be on the right. So this is what this T is going to represent. And then we want to know if we visited S or not. We want to know to not put this back into the queue, because if we keep putting it back into the queue, we're gonna have like an infinite loop going on. So let's create a visited. I'm gonna save myself some space here. Let's create a visited. So let's say visited, and we're gonna give visited. We're gonna make it an array of all false. Let's just use a different color to spice things up. We're gonna give it all false. So all false entries. We'll just start off with all false because we've never visited anything. And we're just going to create that table. Let's say it's the size. It's the size of how many nodes we need. So let's just assume that. Now, let's begin our while loop. We want to repeat some sort of action. Until the queue is fully empty, until we've popped everything out. So to do this, let's just write a simple action and say while, let's give myself more space, while queue is, let's make that more thick, is not empty. It's not empty. So we're going to perform this action while queue is not empty. Now we're gonna take our arbitrary u here. Take our u. Now this is gonna be where we're popping out. So we're gonna fill our queue. We started our queue with S. So let's go ahead and begin to start popping those things out. So we're gonna say queue dot. We're gonna pop out the next entry, pop. So we're taking out this S. And putting it into U. Now we're going to say. We visited. We just visited. We actually just swap up the colors here. Just visited U. Okay, we popped it out. We're beginning to evaluate it. So let's start by marking it off. Let's start by marking it off. So at this entry in the table, at visited brackets U, so we're going to access that entry inside of our visited table. Maybe let's make it a hash table to be more exact. A hash table so we can just, so it's a hash table, so it looks something like this. We can have S is here, and S is currently false. S is currently false, and all the other entries are currently false. You can sort of think about it like that. Think about it like that. This is pseudocode. You can be loose as long as you are communicating, what you are doing. So I'm going to be weird here and put true to be red. So we're going to do true as red. So we're going to put true, and we're going to say, yes, we have visited you. We have visited you. And now we can go and update our table, T, and say, hey, we finally have this entry. Let me see if I can move this guy a little bit over. I'm running out of space. You can say, hey, T, I have an entry for you. Put in this U and give it its own sort of array for neighbors. So it's just going to give it an empty array. And then now we're going to go on to our next for loop. So this for loop down here, we're going to say, okay, all that was just to like pad up this S we just took off. First, we're going through the queue, making sure the queue isn't empty. We're popping out U, so we're taking it out the queue. We took it out the queue. We're saying that we just visited it, so we can't put it back into the queue. And we're updating our tree so we can have a nice tree to end things off. So all that was just to pamper the thing being taken off the queue. Now let's fill up the queue. Let's say for V, make sure that's sharp. For V in, so this G up here, so for V in G, access all of U's neighbors. So what this is going to do, this GU you see here, we're going to have a hash table, and the hash table, let's see, it's going to be A and B. It's going to be set up like this. This is common notation you'll see. We're going to have a hash table. It's going to have entries S, A, then B. And in those slots, we're going to have, okay, S has a neighbor A and S has a neighbor B. So we keep this directed. Let's keep this directed for a moment. And S is going to say, okay, it has neighbors A and B, and then let's say C, D, E, F. And A is going to say C, then D, and then B is going to say E, then F, and then so on. So by saying G, so this right here, this is G, we're saying, okay, input S here. And what this is going to return is this side of the table. So it's going to return us an array. It's going to return us an array of neighbors to possibly go through. So right here, we're basically saying S. Right here, give me the entries of S. So it's going to be like, okay, I'm going to give you A and B. So that's basically what we're getting right there. So let me erase this, make this more clean. Okay, the next part, we're going to iterate all over all of those neighbors. And we're going to say, okay, you're going to say, if, let me use yellow. If not visited, if you've not been visited, so I don't want to put anything back into the queue. That's to stop things like this and things we've already visited. So for visited, if you've not been visited, so if V, this incoming neighbor that we're evaluating, V, let me just give it a different color to not to be super confusing. V's and U's everywhere. So let's give it V. For this V, we're going to ask this V, if you've not been visited, remember this is returning true or false. So this is probably going to return a true, and if this returns a true, it's going to say, no, I'm not going to do this if statement. But if the if statement returns false, not false is true, not false is true. So we're going to evaluate it. And in that evaluation, we're going to do two things. We're going to say, yes, we visited. Okay, now we visited it, or since we've already done it up here, we can leave that step for upstairs, so we don't need to say we already visited it, because we already say that on the line above when we're popping it off the stack. So that's going to save us from accidentally adding it back again. We can say that we can add this t. Since we initialized our u value, since we initialized our t, so our s entry is going to need to say, who are their neighbors? Who are their neighbors? So tu, this is u, not v. We made v green. So now we're going to fill up the entries of u. Add v. We're going to add v here. We're going to add v, and then we're going to insert this puppy into the queue. So insert v. So again, for this for loop, once we've pampered our thing off the queue, so this is the thing getting popped off the queue, we're now going to look at all of its neighbors. Can we put all of its neighbors in the queue? So have you been visited? Have you been visited, neighbor? If it hasn't been visited, okay, good. We're going to add you to the entries for t to build out the tree. So s is here, and now it's going to, this inner for loop is going to start adding those entries. It's like, oh, thank you for adding these entries. And now, let me go back. And now we're going to insert this neighbor into the queue to be evaluated. And that, you can code this up in your favorite coding language. I've stuck somewhat similar to Python, but you can pop this in. Into your favorite sort of coding language, and this will be running BFS on any graph that you give it. So now let's go ahead and do the same thing for DFS. With DFS, let's try it on a simple, binary tree. We know we have some sort of stack. And we know we pre-populate this stack with S. So let's go ahead and start doing that. We know we have a stack. Let's instantiate that. I don't know. Let's just say we instantiate it with stack. So this is a poorly drawn arrow. So this is the stack. So it instantiates the stack. We know we want to keep track of things that are visited. So let's try something for visited. So we want to keep track of visited. Make this some sort of hash table. And let's instantiate everything to, I don't know, false. And then false. Just pretend that says false. And then, we add to the stack. We add S. We throw S in there to start it off. So now let's try to repeat this. So while we have a stack, while the stack is not empty, let's say stack is not empty, while the stack is not empty, what should we do next? Just like the BFS, we want to take the next thing off the stack. Well, how are we representing the stack? We can have item 0, 1, 2, 3, 4. This could be this stack could be like an array, 0, 1, 2, 3, and 4. So we really just want that last element to start evaluating. So It's a bit of Python notation, but I'm going to represent the last element as -1. So to begin, we can say that our u, the thing we start with, the thing that we want to evaluate first, we want to say, okay, u, I want to evaluate you, and we're going to pop u off the stack. So u becomes this thing. We go to stack. We look at the stack, and we're going to look at the -1th entry. So -1th entry is going to be the last entry. So it's sort of like the last entry. We're going to look at the last entry. And in this, we're going to say, okay, so we popped you off, because usually, as we saw before, these could all be visited. Like we could have visited these already. So if you have already been visited, so if visited you, so we're going to access our table here, the visited. So we want to check if u is already visited. If we're looking at the stack and we say, oh, this u has already been visited, we want to take that off the stack. We don't really care about this. We don't want to evaluate this anymore. So let's just say stack.pop. That's when we actually say, oh, goodbye, we don't really care about you. You pop it off the stack. So now let's continue. Let's say else. So what you do else, we want to start running our sort of algorithm of traversing or adding the next children to be visited. For this, let's start cramming some space here. So let's say visited. So now that we have u, we want to make sure that u is set to already visited. So we haven't visited it. We said we haven't visited it already. So let's say, okay, fine. We have now visited you. So you're now true. And our next step is to say, and start to adding these children in. So again, just like our breadth first search, we're going to say for, let me use a different color. We're going to start populating. So we're going to say, okay, for v, let's use that different color again, for v in different colors, for v in g, and we're taking that u, the thing we initially popped off, we're taking that u, and we're going to say, okay, to populate u, to make sure, okay, have you not been visited? Just another check. So if not, and we make this white, visited. So if we haven't visited you at all, let's add you back into the stack. Let's add v back into the stack to make sure we aren't repopulating things we've already visited. And if this is true, if you've not been added to the stack or you haven't been visited, let's say stack dot add v. That is how to perform DFS with a stack. So now say we wanted to run DFS on this binary tree, So we know it is directed. We know it's directed. We want to go left and right. If I were to draw the table out right here, we would have S, A, B, C, and so on. And the entries for this table, there will be two entries. There's going to be the left entry and the right entry, left and right. And if we're speaking about arrays, the 0 indexed array will be the left, and the 1 indexed in the array is going to be the right. So we're going to have A, then B. So if I were to call this graph G, if I wanted to access the left and right, down here I would put S, and then which one I would like to access. So if I wanted to access the left, I would put 0. Then if I wanted to access the right, I would put 1. So we see that if we want left, there's left and right, and if we want left, we put 0, right, we put 1. So we're going to use this for DFS, and we're going to traverse this binary tree, left and right, and then we're going to mix up the orders. So first, we're going to take our input. We're going to do this recursively. We're going to take in our tree, G, and we're going to take in the node that we're going to start with. So we're going to just an arbitrary U. Now, just to account for when we get to the bottom here and C is going to return no children, we want to account for that case. So we're going to write an if statement here at the beginning. We're going to say if U is null, so if U is null, I want you to return. So if U is null, just return. Don't do anything at all. Then we're going to have two recursive statements where we call DFS again, We're going to return G because we need G. Now, here's the magic. We're going to say, okay, we're going to return the new node to run this on, to traverse on. So now, we're going to say, okay, we're going to say we need U. We start with U. Use the right color. So we're going to access U, and we're going to access the left. We want to go to the left and to the right. What are we going to put in here? We're going to put 0 for left, then 1 for the right. So how this is going to work, our computer is going to take care of this sort of stack behavior for us. So we have the stack here. We're going to first start the stack by calling S. We're going to first throw S in, and then your computer is going to be like, okay, I'm working on S. And then it's going to hit, it's not going to be null, so it's going to hit this first statement, and it's going to, okay, now it's going to call A with this function. So it's going to say, okay, I'm going to take a break on this. I got a new function call. Let me take care of that function call. A is going to then hit the same left. The computer's going to be like, okay, let me take care of this first. And then finally we're going to get a return statement here. Since it's null, we're going to get a return statement. The return statement's going to tell us, okay, now we're going to finally hit this right. After we returned from this left, we're going to return from here, and now we're going to finally be able to execute this sort of next statement. So we're going to execute this next statement. It's going to return null again since there's no entries for the right. Pop back up. And we're finally going to return from this statement. There's nothing to do. We're done with this. function. So what's going to happen, we're going to pop back off the stack. Now A is going to have a chance. So from A's perspective, we just returned from the left. Now we can go ahead and start going on the right. So that's how the stack is operating here. Our system is taking care of it for us. Though it is more cost efficient to write out the stack yourself, but this is how recursion is working under the hood. So now let's give ourselves, let's say we're going to process these nodes in some particular order. Say we have a print statement. We have a print statement here, print. And we're just going to print U. And we're going to say that we're going to process U at this time. So now let's take care of that right here. So if we first, run through, we put S, we hit this print statement, and we put S here. We're going to put S. Now S is going to call the left. Now it's going to call the left. Now before it traverses again, we're going to print. So we're going to print, and then we're going to call to the left again, C, and then we're going to call left. There's nothing. Right, there's nothing. We return. We call it to D, and D, before we traverse, we print D, so going to left, return, right, return, 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 we're all the way back up at S. Now, see if you can pause the video to see if you can guess what's going to happen next. Okay, so now we're going to go down to B before we traverse, print B, go to E before we traverse, it's E, and then go back, you see the pattern, we're going to traverse back up, and then F before we traverse again, and then that will be the traversal. We're going to go left, right, right, and come back all the way up, return, return, return all the way back up. This is called pre-order traversal because we're evaluating it preemptively before our print statements, before our recursive statements, before our recursive statements. So this is pre-order. Now there's a couple more. There's post, there's in order, and we're going to do that right now. And then there's level order traversal, So we're going to do, let's do in order. So in order is when we put DFS, put a little bit below, and we put the print statements in the middle. This is in order. So let's process this. So we start with S. So we're going to evaluate this after we returned from the left. So let's do that. So we're going to go to the left, A, left. Okay, we returned finally from the left. So C. So we're going to do C. We finally returned from the left. We're going to do A. We're going to go to D, go to the left, return from the left, print D, and then go to the right, and then pop back up from the right. And we returned from the left. We're finally going back to S. We're going to print S. We're going to go down the tree again. So to the left, return from the left, E, return from the left, we print B. We go to the right, we go to the left, return from the left, we print F. And we finally return all the way back up the tree. This is in order traversal. Now for post-order traversal, we're going to put this print statement right after our traversal. So we're going to put this print statement right after. So after we return from the right, then we're going to print. So again, we start with S, left. And now we return from the right for C. Now we're finally going to print C. So we're going to print C. And then we go to A. Then we go to D. From the left. From the right, we return from the right, we print D. Then we return from the right, we print A. And then we're returning from the left. We go down, go to B. We go to E. And again, we're going to return from the right on E. Return from the left, go to F, to left. And we'll return from the right for F, return from the right for B, and finally return from the right for S. So this is post-order traversal. We have one more, which is level order traversal. Now, level order traversal is just BFS. Because we're evaluating it at every level. So how do we perform BFS on a binary tree? So first of everything, the most important thing we're going to need is our queue. So we're going to need some sort of queue. And remember, we populated this queue. With queue.add our starting node. So in this case, it'll be U. So our first entry is going to be U, and then we're going to say while. We're going to use some shorthand notation. While Q. If we say while Q, so if it's full, if it has items, it's going to evaluate as true, so truthy. If it's empty, it's going to evaluate as false. This happens in a couple of programming languages. So if it's false, so if it's empty, it's going to evaluate as false. So we can say while Q. Now let's call this S to not confuse, so we can start using V. So let's call this S, so our starting node. Now we're gonna take V, We're going to take v or u, confusing my u's and v's again. So we're going to take u, we're going to take this, our first thing off the stack. So we're literally just performing BFS. So we pop this off, and at this point we can print, so we print, and then we're going to say, I'm going to need some more space here. I'm going to move. So now we're going to say, we're going to need our left. First we're going to need the left. Then we're going to need the right. The right. So this is going to be, so we're just going to access the left and right again. So we're going to do it breathly. We're going to queue both of these. We're going to queue both of those. So again, we're going to say left, then right, and we're going to call G. Guess what we're going to put in here? We're going to put our node. And then we're going to say left, then right, left and right. Now the final check is going to be, we're going to say, okay, we have left and right. Now, if there is a left, if left isn't null, it's going to evaluate as true. We're going to add left to the queue. So we're going to q.add left. And then if right, so if we do have a right, it's going to evaluate as truthy. If it's not null, we're going to say q.add right. So now this we're just going to get our standard in order or level order traversal. So if we said level, so if we were to trace this, we would put in S, we'd start with S here, and then we'd go level by level from left to right. So we go S in our Q, then A, then B, then C, then D, then E, then F. So these are our level order traversals. These are the types of traversals you can get in a binary tree. For pre-order, we print before we traverse. So for DFS, we print before. In order, we print in the middle. So after we return from the left. Post, we're doing that after both left and right recursive calls. Level order, we're just running BFS. And with that, thank you. This is the end of the video. If you enjoyed it, don't forget to like and subscribe. If you want more content, more examples, and a concise rendering of this video, you can go into the description, and there's currently an open source textbook that is being worked on to try and consolidate all of this information into one place. So if you're interested in that, you can go ahead and click in the description below. And this is open source, so if you see any grammar mistakes, if you want to add anything, you are free to do so to contribute towards the community. And with that, thank you.